Welcome to Stereochemistry 4, Part 2. There are two types of reactions that involve stereochemistry. You can see them here, regioselective reaction and stereoselective reaction. The regioselective, we've talked about that before, is preferential formation of one constitutional isomer over another. And it's shown here if you have A forming B plus C, more B is formed than C, where B and C are constitutional isomers. Stereoselective reaction is preferential formation of a stereoisomer. Notice stereo is in front of the stereoselective. So again, A forming B plus C, more B is formed than C, where B and C are stereoisomers. So we call that stereoselective. Regioselective. Regio tells us constitutional isomers. Stereoselective. Stereo tells us we're talking about stereoisomers. So remember, constitutional isomers have the same molecular formula, but the atoms in each compound are connected differently. With stereoisomers, the molecular formulas and the way the atoms are connected are the same. The arrangements in space is different. Regioselective reactions can be moderately, highly, or completely regioselective. Reactions can also be moderately, highly, or completely stereoselective. Okay, let's go to the next slide. There we go. Okay, stereospecific reaction. Each stereoisomeric reactant produces a different stereoisomeric product or a different set of products. A forming B, C forming D. A and C are stereoisomers, B and D are stereoisomers. All stereoselective reactions are not stereospecific because there are stereoselective reactions in which the reactant does not have a carbon-carbon double bond or an asymmetric carbon. So it cannot exist as stereoisomers. Now, let's combine our knowledge of alkene reactions with stereochemistry. You remember me telling you that we were going to do this. And the rest of Chapter 5 is somewhat of a review of Chapter 4 with stereochemistry added. Most of the ACE homework is alkene reactions, but with stereochemistry included in Chapter 5 homework. Also, alkenes with stereochemistry is in the practice problems for Chapter 4. At least intermittently they are. Some of the problems are like that. Earlier we learned that when an alkene reacts with electrophilic reagent like HBr, the major product of the addition reaction is the one obtained by adding the electrophile, the H plus positive proton, to the sp2 carbon bonded to the greater number of hydrogens, and adding the nucleophile, the negative bromine ion, to the other sp2 carbon. Here we've got 1-butene. There is no asymmetric carbon in this compound. We've added a proton to the sp2 carbon with the most protons, so now it's at CH3, and we've formed a carbocation. We're going to see this on the next slide. Here's the nucleophile coming in, bonding to that site, the electrophilic positive site, and creating a chirility center. Of course, that is an asymmetric carbon right there. Does the reaction on this slide create a product with an asymmetric carbon? Yes, as we just pointed out. So what is the configuration of the product? Is it the R enantiomer or the S enantiomer? Or is it both enantiomers? We will look at reactions that form a product with one asymmetric carbon, and then we will look at reactions that form a product with two asymmetric carbons. Let's proceed. As it turns out, when a reactant that does not have an asymmetric carbon undergoes a reaction that forms a product with one asymmetric carbon, the product will be a racemic mixture. So the reaction of 1-butene with hydrogen bromide, forms identical amounts of the R2-bromobutane and S2-bromobutane. In this case, the reaction is not stereoselective because it does not select for a particular stereoisomer. So you can see here, this is the carbocation formed in the first step of the reaction shown. And the addition reactions that form, it's going to form one asymmetric carbon. If the nucleophile bromine approaches from this direction to the positive side of the carbocation, we will have the S product. If it approaches from below, then it results in the R product. The illustration on this slide explains why a racemic mixture is formed. Examine the structure of the carbocation formed in the first step, as we can see here. The carbon with the positive charge is sp2 hybridized. So the three atoms that it's bonded to line a plane, and there is an empty p orbital. When the bromine, as you can see, approaches from above the plane, we get one enantiomer. When it approaches from below the plane, from the other direction, the other enantiomer is formed. Identical amounts of R and S enantiomers are formed. Here's an example of a reaction that has a reactant with one asymmetric carbon that results in a product with two asymmetric carbons. Here's the one asymmetric carbon right there. And it's going to form two asymmetric carbons, this one and this one. Of course, this is the one it had to start with. So it has a new asymmetric carbon right there. But the product has two asymmetric carbons. The reactant has one. If you take a compound with one asymmetric carbon already and take it through a reaction that gives it another asymmetric carbon, a pair of diastomers will be formed. Diastomers are stereoisomers that are not enantiomers. They're not identical, and they are not mirror images. One asymmetric center is the same, but the other one is not. Take a look at the above reaction again. None of the bonds to the asymmetric carbon in the reactant is broken during the addition of HBr. There it is right there. There it is in the product. So the configuration of this asymmetric carbon does not change. However, the bromide ion can approach the planar carbocation intermediate from either the top or the bottom in the process of making the new asymmetric carbon. Two stereoisomers result. There are only two because one of the asymmetric carbons has the same configuration in both isomers and the other has opposite configurations in the two isomers. These two have the same, and then the other possibility is that this would be different. The second one will be different. Now you'll notice down here we have the stereochemistry of the product illustrated using a different display method. And here are the asymmetric carbons, one there, one here, one here. These are the same, this one and this one. These are different. That one is different from that one. They're not mirror images. They're not identical. Okay, addition reactions that form products with two asymmetric carbons. We're going to see that, number one, addition reactions that form a carbocation intermediate. This is like our alkene reaction number one. Stereochemistry of hydrogen addition we're going to look at. This is like alkene reaction number 10. Stereochemistry of peroxy acid addition. This is alkene reaction number 8. Number 4, stereochemistry of hydroboration oxidation. This, of course, is alkene reaction number 9. The addition reactions that form bromonium ion intermediate. This is alkene reaction number 4. You know these, but now we're going to add the stereochemistry. We will now look at these 5 types of reactions. Each one you have seen before, but this time we're going to be looking at the stereochemistry. So this is somewhat of a review. Let's look at the first one here before we conclude. Here's the first type of reaction. It involves a carbocation intermediate. This is like alkene reaction number 1. This is the case when a reactant that does not have an asymmetric carbon undergoes a reaction that forms a product with 2 asymmetric carbons. Notice here, cis, this compound is cis-3,4-dimethyl-3-hexene. It does not have a single asymmetric carbon, whereas here in the product, we have a compound known as 3-chloro-3,4-dimethyl-hexane that has an asymmetric carbon right there, and also this one. So we have 2 asymmetric carbons in the product. So I've shown the 2 asymmetric carbons in the 3-chloro-3,4-dimethyl-hexane product. They're formed from the cis-3,4-dimethyl-3-hexene reactant by the addition of hydrogen chloride. The 4 possible stereoisomers that can be formed are shown above in the perspective formulas. Here they are, these 4, 1, 2, 3, 4. In the first step, the proton can approach the plane of the double bonded carbons of the alkene from above or below to form the carbocation. Now the chloride ion can approach the positively charged carbon from above or below. So 4 stereoisomer products are possible. The proton and the chloride ion can add from above, 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 below, below, above, or below, below. Okay, because we've got 2 steps. When 2 substituents add to the same side of the double bond, the addition is called syn addition, S-Y-N addition, the 2 on the left, these right here. When 2 substituents add to opposite sides of the double bond, the addition is called anti-addition, the 2 on the right, as you can see here. The 4 stereoisomers formed from the cis-alkene, this is the cis-alkene, are identical to the 4 formed by the trans-alkene. Therefore, this reaction is not stereoselective. It's not stereospecific, is what I mean to say. 2 substituents added to the same side of the double bond, syn. 2 substituents added to the opposite sides of the double bond, anti. And we'll be using this terminology again and again. These 2 are syn addition, and these 2 are anti. Notice syn, we have chloride and the proton both pointing towards us, one added at a time during this 2-step process. And here's the proton, and here's the chloride again. And notice these 2 are anti. The chloride behind, this one's pointing towards us, the hydrogen, here's the hydrogen, and the chloride opposite, anti each other. Thank you. This concludes our talk on stereochemistry, part 4.